Hello again, students. I'm back. Now it's Friday morning, and I'm picking up where we left off with example problems for simple harmonic motion. As I was reviewing the video I made, I thought it would be nice to have a sort of one-shot deal of the things we've discussed about simple harmonic motion so far. And I'll take a screenshot of this and post it separately on Canvas. So the things we've talked about, the useful things we need to know about simple harmonic motion so far, is that the simple harmonic motion needs to be driven by a restoring force. For a mass on a spring, that restoring force is Hooke's law. For any other simple harmonic type motion, we should find a force that's equal to negative of displacement from equilibrium times some kind of constant. For springs, specifically, mass on springs rather, the period of the oscillation is 2 pi times the square root of mass over the spring constant. In general, period is always equal to the inverse of frequency. In general, frequency, like the sort of frequency in hertz, I don't know what else to call it, is equal to the angular frequency, omega. So that's frequency in radians per second divided by 2 pi, because one cycle equals 2 pi radians. Specifically, and maybe we need some kind of arrow over here, for a mass spring system, the angular frequency, because of the period being 2 pi square root of m over k, angular frequency becomes square root of k over m. This is always the case for a mass spring system. We developed equations for the motion of simple harmonic motion. That's redundant, but we developed equations for position, velocity, and acceleration with respect to time. The position equation is sinusoidal. If you displace the object from equilibrium and release from rest, then the equation of motion is amplitude times cosine of omega t, where omega again is that angular frequency. However, we've also now started to see an example where we can switch a cosine with a sine as appropriate based on the initial conditions. We'll talk more about that later. If position is a cosine omega t, then the velocity function needs to be negative omega a sine of omega t, and omega a is the maximum velocity, as we discussed when we looked at conservation of energy. So the velocity with respect to time is negative v max times sine of omega t. Again, if the cosine function for position needs to be a sine function based on initial conditions, then this sine function will become a cosine function and will change the sign. The reason for that is derivatives and calculus, and we're not really going to go there, but if you are familiar with calculus, you know that you're taking the derivative of the position function to get velocity, you're taking the derivative of the velocity function to get acceleration, and these are derivatives of sinusoidal functions. So aside from that, finally, our acceleration function with respect to time, acceleration is equal to force over mass, gives us negative omega squared a cosine of omega t, and omega squared a is the same as maximum acceleration. So negative maximum acceleration cosine of omega t. In general, maximum velocity is omega a, specifically for a spring mass, since omega is square root of k over m. Spring mass omega, angular velocity, tangential or linear velocity is square root of k over m times a. In general, the maximum acceleration is omega squared a, specifically for a spring mass system, that's k over m times a. And then, as we discussed energy, we developed the equation for velocity with respect to the object's position. So we have an equation for velocity with respect to time. This is velocity with respect to position. These are useful equations. So velocity with respect to position is plus or minus v max, right? We have to vary between those min and max velocities, times the square root of 1 minus x squared over a squared. And we developed this equation again by considering conservation of mechanical energy. So as I said, I'll take a snapshot of this, but I will refer to this because I think this is going to end up being quite a useful thing to have. Okay, so I was interrupted at the beginning of part B of number 8. So in part A of number 8, we found an equation for position for a vertical spring with stiffness constant 305 newtons per meter, oscillating with an amplitude of 0.28 meters, so 28 centimeters. So there's my amplitude, when 0.235 kilograms hangs from it. So we found the angular velocity, right? We found the angular frequency. We kind of use angular velocity and angular frequency we use interchangeably. They really do mean the same thing, radians per second. So we found that omega by finding the square root of k over m. K was given, m was given. And then we picked a sine function instead of a cosine function because we're told that the mass passes through equilibrium, y equals 0, with positive velocity at t equals 0. And so just thinking about how the shape of the graph should look, time is on the x-axis and position is on the y-axis. At t equals 0, so at this moment in time, I should have, oh, it's not x though, it's a vertical spring, so that's y. I need to have position equal to 0, and I need to have the velocity, so the slope of the line being positive. And so then I thought about how that object would oscillate up to its peak, pause, and then come back down to equilibrium, oscillate down to its bottom, and come back up to equilibrium. And the shape of that function is a sine curve. So I chose a sine instead of cosine. Part B, at what times will the spring be longest and shortest? So I want to know what time t is the spring maximally sort of compressed, and at what time t is the spring maximally stretched. All right, we're thinking about literally vertical oscillation, up, down, but we're stretching it out over time. So what is this t and what is this t? So using the equation we developed in part A, I want to say, what time is it when the position is plus amplitude? What time is it when the position is minus amplitude? So let's start with plus. We'll start with our first time. So my position at this moment needs to be 0.28 meters. And 0.28 meters equals my function, 0.28, times sine of omega 36t. Dropping the units just to be sort of clearer with the algebra. Okay, so I'm solving for t. T's inside the sine. I need to isolate sine. This goes away. This becomes 1 equals sine of 36t. Now I need to take inverse sine of both sides to get the time out of the sine function. So sine -1 of 1 equals sine -1 of sine. I'm just trying to show all the steps here because sometimes we get a little flummoxed with the algebra involving sinusoidal functions. Okay, so inverse sine of sine gives me 36t, and then inverse sine of 1, I should probably know this, but I don't. What is that, 90 degrees? You know how I feel about the unit circle and how I cheated in high school, and you're not going to follow my example. So I'm finding the inverse sine of 1 just to be sure because it's Friday morning, and when you're carrying out, now here's an issue, right? Here we are with radians per second, and we're dealing with a sine cosine function in radians, and I've just carried out my calculation in degrees. This is not going to work because if I say inverse sine of 1, over here I'm going to have an answer that's in degrees, and then on the right hand side I'm going to have a unitless answer. Radians per second times seconds is radians. I can't compare those two. So now I have to figure out how to get my calculator into radian mode, and this is when this actually matters for us, and we'll start questioning ourselves. There we go. Okay, I'm in radians now, so let me try that again. So I've got inverse sine of 1.57 radians. Okay, so 1.57 radians. I've kind of done my unit check, and I'm trying to figure out at what time does this occur, and so I'm dividing by 36 radians per second, right? And you'll see I'm dividing by 36 radians per second, so I have radians divided by radians per second. I'm being very careful with my units, so that I have 1 over 1 over second. So 0.04, let's call it 4 seconds is equal to time. All right, so we found the time when our position function is at its positive max. So that's when the spring is that's when the spring is shortest, right? Because the spring is literally like up here attached to the wall. So the spring is the most compressed here, and the spring is the most stretched out here. All right, so I don't know how much more of the solution you need to see, but let's just finish the thought. for the longest point, the spring is going to be at negative 0.28 meters, right? So it's at its negative amplitude, and that's equal to 0.28 sine of 36t, okay? And so same process, divide by 0.28, divide by 0.28. The difference here is that now I have negative 1 is equal to sine of 36t. And so I find the inverse of negative 1, or rather inverse sine of negative 1, which again is something I should know, but I don't. And so, it's negative 1.57, etc. radians. That's equal to 36t. And so we find t is equal to negative. Ooh, wait a minute, that's not going to work, right? Because I'm going to get a negative time. That's telling me this time back here, right here. So we have a little issue here, right? What is this time? What is this time? Oh, we didn't have to actually solve this, did we? Because we know how sine and cosine functions work. This gave me the sort of the time before we started measuring, but I know that this time from equilibrium to equilibrium is one complete period, and I know that the period is equal to 2 pi square root of m over k, right? I mean, that's what we found for springs. So I know that this is half a period, this is 3/4 of a period, this is half a period, right? From peak to trough, I have half a period. So I can just find half a period, t over 2, is 2 pi square root of m over k. This is the same thing as 2 pi over omega, and so I'm going to say 2 pi over 36 radians per second, but I do need to divide by 2, right, in all of this. Divide by 2, divide by 2. I realize I'm getting messy, but we can talk about this more in class. So I'm finding that half a period is a time of pi divided by 36, so a time of 0.087 seconds. And I found my first spot here where the time where the spring is maximally compressed, the time where the spring oscillation is at its positive amplitude. All I need to do to find where it's at its negative amplitude is add half a period. So, 0.044 seconds plus 0.087 seconds. And that's a lot easier than trying to solve this sine function. We can sort of think around it. If I can add these two decimals together, 131 seconds. Good enough, right? So that's a nicer solution, I think. Okay, now we're going to have some algebra with trig functions, and that's going to be a stumbling block, and that's okay. We'll keep practicing. We're going to have to really conceptually understand how our motion maps onto these trig functions as well, and that's another stumbling block. So again, we're just going to need a lot of practice, kind of managing how does this movement look in real life, and then sort of how do we map this onto a position versus function graph. And we had this problem, we experienced this issue at the very beginning of the year when we were trying to map a sort of linear motion onto graphs of position versus time and velocity versus time. So be patient with yourself. We're mapping a different kind of motion, but the mental process is real similar. We're saying, okay, where is this thing at t equals 0? How is it moving? Which direction is it moving? How does that influence the shape of my position versus time graph or my velocity versus time graph? Using what we know about slopes and signs of slopes, and then adding in what we know about trig functions. Let's look at number 15 for an example now. So we have a 0.25 kilogram mass at the end of a spring oscillating 2.2 times per second with an amplitude of 0.15 meters. I like that we have a lot of information. We need to determine the speed when it passes the equilibrium point, and then the speed when it's 0.1 meters from equilibrium, and then the total energy of the system, and then the equation describing the motion of the mass, assuming that at t equals 0, x was a max. So I can kind of already start to visualize this motion, okay? I have a block on a... It actually doesn't tell us whether it's oscillating vertically or horizontally, so whatever. We know that the sort of mathematical description is the same either way. I have a mass on a spring. I'll assume that it's moving horizontally, and I know that it's oscillating between its max and min positions. with this distance being equal to the amplitude, and of course this distance being negative amplitude. Let's see, we actually know that the amplitude is 0.15 meters. We know that the mass is 0.25 kilograms. And we know that it oscillates 2.2 times per second. So number of oscillations per second is frequency in hertz. So 2.2 oscillations per second is frequency. But that lets me know also the angular frequency. Because again, from my useful things to know about simple harmonic motion, angular frequency will be 2 pi times frequency in hertz. So 2 pi times f. I suppose I could leave it as like 4.4 pi if you like, but I'd prefer to have like digits. 2.2 pi is, 6.911. No, 6.912 if I'm rounding correctly. And instead of hertz now, my units are rad per second. I want to be really clear about my units, and I want to check my calculator units, and I want to make sure that when I'm entering quantities into those sinusoidal functions that I'm having unitless numbers. Okay, so part A, what's the speed when it passes equilibrium? Well, I know however this thing starts out, whenever the block passes through equilibrium, the spring is at equilibrium, the acceleration is 0, and the velocity is maximum. So it's asking me for the maximum velocity. Vmax always at equilibrium. And so again, back to my useful things for simple harmonic motion, I know always that maximum velocity is omega times amplitude. Okay, so that's not so bad. Vmax is plus or minus omega A, and I have now figured those out. 6.912 radians per second times 0.15 meters, right? And again, checking those units, I've got meters times radians, but radians are unitless, so meters per second. So that's good. It's a good check. I've got units of expected meters per second for velocity. And my max velocity then, according to the given quantities, is 46.08 meters per second. See that this camera keeps keeps getting it out of focus. I'm not sure how to fix that. All right, so that's A. B, the speed when it is 0.1 meters from equilibrium. Okay, so now we're no longer at equilibrium, right? 0.1 to the left or to the right is not going to matter because it's symmetric. So V at x equals 0.1 meters. It's not asking me for the velocity at a particular time. It's asking me for the velocity at a particular position. And I remember that using conservation of energy, we developed an equation for that. The velocity at a particular point in the oscillation is plus or minus V max times the square root of 1 minus x squared over a squared. So V is equal to plus or minus V max, so 46.08, times the square root of 1 minus x squared, so the position we're interested in, 0.1 meters squared, over amplitude squared, max min, 0.15 meters quantity squared. And so we find that the velocity is equal to, here, I'll show you my calculation. You can track whether or not I do this correctly. So we're doing 0.1 squared, actually I don't know where my squared button is, divided by 0.15 squared, and then I'm going to subtract that from 1, and then I'm going to take the square root of that, and then I'm going to multiply that by 46. So this gives me basically a percentage, right? What percentage here of my maximum velocity? So it's about 75% of my maximum velocity of 46.08. 46.08, 34.35 meters per second. This business here is percentage of velocity based on its position. Okay, C, what's the total energy of the system? Well, again, coming back to my, maybe I didn't actually write that one down. But coming back to the useful things to know, which I need to add to useful things to know, is that the maximum energy occurs at, so I have Emax either at maximum kinetic energy, so half times mass times max velocity squared, or at maximum spring potential energy, half K times A squared. Let's see, I know A, but I don't think we're not given K outright, but we are given mass outright. So just being lazy, since I now know V max, I'm going to go with max kinetic energy. 0.25 kilograms times 46.08 meters per second, quantity squared. Of course, since we actually know mass and now omega, wherever omega went, we could calculate the K value because we know omega is equal to the square root of K over M, but that seems like unnecessary. Yeah, unnecessary unless someone makes me do it. So I'm dividing 0.25 by 2, and I'm multiplying by 46.08 squared. And I have a max kinetic energy, which equals the maximum energy in total of 265.4208. So let's call it 265 joules. Finally, I want to develop an equation for the position, for the motion, an equation describing the motion of the mass. That usually means a position equation. Position with respect to time, assuming that at t equals 0, x was a max. So I'm thinking again about trying to graph it, trying to visualize it. T is on the x-axis. Now I have a horizontal motion, so x is on the y-axis. We love that. Okay, so at t equals 0, x was a max. So I either have x up here or x down here. So I either have a positive cosine function or a negative cosine function. They don't really specify which, so being lazy, I'm going to choose positive cosine function. Position is at a max, velocity is at a min, so I should have flat line right there. And then the velocity increases in the negative direction until I get to equilibrium. The velocity decreases to 0 at the negative maximum position. The velocity then increases in the positive direction until I get to equilibrium. And then velocity decreases again momentarily to 0 at the maximum displacement again. So cosine function. So I'm expecting my function to look like x equals constant times cosine of different constant times time, right? But we now know from our investigation into simple harmonic motion that the first constant there needs to be the amplitude. We're told the amplitude is 0.15 meters. And then cosine of the constant inside, the stretching a long time constant, is omega, is our angular frequency. So omega, as we calculated, was 6.912 radians per second. I don't want to have to write all those digits. I'm going to round to 3 sig fig, 6.91 t, close parentheses. Shoot, I have units here. I didn't put units here. This is rad for a second. Maybe I want to have there. That's getting messy, but you get the picture, right? Amplitude times cosine of omega t. Okay. So now we want to have one more example. And I am on the wrong thing here. All right. So number 21, right? We're sort of expecting more complex examples as we go along. Figure out how to make the screen lighter. All right, so number 21, Agent Arlene devised the following method of measuring the muzzle velocity of a rifle. She fires a bullet into a 4.148 kilogram wooden block resting on a smooth surface and attached to a spring of spring constant K equals 1.62.7 newtons per meter. Of course she does. The bullet, whose mass is 7.870 grams, remains embedded in the wooden block. I sense a collision here. It remains embedded in the wooden block, and she measures the maximum distance that the block compresses the spring to be 9.460 centimeters. What was that incident speed of the bullet? Ooh, okay. So I sense a collision. Especially look at that picture. We have little m of the bullet before the collision and its starting velocity, and big M of the block, and then afterwards we have m plus m. That should sort of trigger in your mind the idea of an inelastic. Oops, I have to be able to spell inelastic though. Inelastic collision. right? We have one thing moving and another thing not moving, and then they collide and they stick together. The bullet remains embedded in the block, and then something else happens. So we're going to have, again, as usual with AP Physics, we've got a kind of two-part thing. We have a collision that occurs, right? A collision between bullet and block. And then we have something else happening, right? The bullet block now compresses a spring. What could I use to think about the compression of the spring? Because this makes me want to think about conservation of momentum. I will have something moving on a frictionless surface, and I'll know its mass. So moving to compressing. And the thing that comes to mind there is moving to compressing. That makes me feel like energy and conservation of energy. So I'm going to see if I can solve it with conservation of energy. So I'm thinking in my two ways here. Conservation of momentum, that looks like mass of the bullet times the bullet's starting velocity. So lowercase m as shown in the diagram times v plus no momentum in the block equals block plus bullet traveling at, what do I want to call it? I'll call it v naught because this is the after collision speed. So before the collision, momentum before is totally held in the bullet because the block's not moving. Momentum after is held in both the bullet and block because they're stuck together, going together. I get that V naught is sort of like supposed to be before. We could just call it V2 if that bothers you. V2, V prime, whatever. It doesn't matter because we're going to have another velocity, or no, we're going to use it again. Okay, so let's say we kind of use this to find a relationship between V2 and V, and then I'm going to link these together because I'm going to think, okay, before the collision, or rather just after the collision, so we have an E1 after collision, two separate events, right? Collision, then spring. So after the collision, I have energy in the bullet block, and then that energy in the bullet block gets switched to compression. So after compression, I don't need to think about gravitational potential energy here because everything's happening on a horizontal frictionless surface. So directly after the collision, I have a bullet block moving and spring not yet compressed. The spring then gets compressed. So kinetic energy gets transformed into spring potential energy. Half, I'm going to say m plus m because they're together, and that velocity is the velocity of the bullet block after they have the collision squared equals half k displacement squared, right? Half kx squared. I don't know why I needed to write it as a delta x squared. Now let's see what we know. So we do know k. K is 162.7, right? So like sort of, yes, I know that. Do I know how far? Yes, right? The spring compresses 9.460 centimeters, so I know that. I know the mass of the bullet and the mass of the block. I know that. I don't know the velocity before or after the collision, but look at this. So I don't know V2. So here I have one equation and one unknown. And then over here, I have one equation. I know mass, rather. I guess I'm putting a squiggly line for things I don't know. Check mass, check mass. I don't know either of these velocities, but I can use conservation of energy to figure out what the velocity of the bullet block is as the collision, or rather right after the collision. That can go here right after the collision, and then I can find the velocity before collision. So I'm going backwards in time to figure out the velocity of the bullet. Awesome. Okay, So now we just need to sort out like sort of masses and stuff, right? All the hard work is done. We've done all the thinking about the physics. What do we know? The mass of block is 4.148 kilograms. I'm going to figure out what m plus m is first. Oh, no, you can see that. I had to come up here because I know I'm running out of room. Or no, what I'll do is, I'm running out of everything. That's what we'll do. We just want the big idea here. Or why am I not writing on this? I don't know. It's Friday morning, you guys. All right, here we go. All right, what is our mass? We have m plus m of 4.148 kilograms, and that bullet has a tiny mass of 0.007870, right, because it's in grams, or given in grams. I totally can't handle this without a calculator. 4.148 plus 0.00787, so 4.15587. What the heck, I'll just leave all those digits. And then, and I can say m, little m of the block, of course, 0.00787. What else do we need to know here? Spring compression, x, or delta x, I'm not being consistent, is 9.460 centimeters. So we're going to call it 0.9460 meters. All right, so now I'm going to work with my energy equation. Okay, half times total mass, 4.15587. I'm in the mood to not use units because everything's SI units. V2 squared equals half times K. K was given to us as, oh, why did I write a K? K was given to us as 162.7 newtons per meter. Again, SI units. And then delta X is 0.0946, and that gets squared. Super. I am tempted to just be lazy and let you guys deal with the rest of this, but just for argument's sake, let's continue our solution. You can fast forward or stop now if you've got the idea. You choose. So 2.07793. Why am I using all these digits? V2 squared equals all this business, the kinetic energy, or the spring potential energy. 162.7 and 0.946 quantity squared. Oh, I got a syntax error. Oh, goody. Goody job. Let's see. I cannot track where I have my error. So that's fun. I'll just clear it. What did I have here? I have to start over because I got a syntax error. On the right-hand side, I'm calculating the spring potential energy due to the compression of the spring after the bullet and block run into it. Okay, on the right-hand side, I have 0.728 joules. Now I'm starting to round. V2 squared then equals, I wasn't using units, but whatever, 2.077 and some stuff. And so V squared is 0.350354 and some more digits. So V2 is 0.592 meters per second. All right, so we've evaluated the conservation of energy side of our idea to find the velocity of the bullet and block just before, or rather just after the collision and just before the spring starts getting compressed. Now I want to go back to my idea for conservation of momentum, now knowing this velocity, to work backwards and find the initial velocity, the sort of incident velocity of the bullet. So here I'm saying mass of the bullet, which again is 0.00787 kilograms, times its incident velocity, that velocity that I wanted to know, is equal to the combined mass of bullet and block after the collision, 4.15587 kilograms, times the velocity that we now know after the collision of 0.592 meters per second. So conservation of momentum now, momentum before the collision all held in the bullet, momentum after the collision held in the bullet plus block. And I solve for velocity. So divide 4.15587 times 0.0592 by 0.00787. And I have a bullet incident velocity of 312.56. So we'll call it 213 meters per second. Not super surprised that we have a very large velocity of the bullet because it's a bullet, for heck's sake. Once that bullet collides with the, 100 times, almost 100 times more massive block, the whole thing slows way down. That's also not surprising. This is a reasonable velocity for a bullet. And that is the end of my example problems for this first section of simple harmonic motion lecture modeling examples. The next step will be to look at pendula, and the ways that pendula do and don't follow simple harmonic motion rules. The end. Don't forget to like and subscribe and whatever I'm supposed to say at the end of a YouTube video. I hope you all have a nice weekend.